Sure. Good.
Very, very important.
Thanks, God.
Hey.
Well, the market's up, but not if I have to sit through this.
Yeah, never mind.
That's all right.
Doris. We can do it.
Good night. Good night.
Still have 2 minutes. If you guys want some more frames, please go ahead.
You don't have to finish in 2 minutes, but just. Yeah, we'll start Michigan Tech time 5 after, so.
Thanks a lot, everyone, for coming here.
Glad to be here.
Glad you got a bigger room.
Yeah.
No. Oh, fine.
Yeah. That's much fun.
Should we talk to you guys? Right after this?
Thank you.
Okay.
October 2017. But I got tracked into another project, so there were 2 projects at the same time.
Are you getting 2 master's degrees? I mean, you got 2 different departments and 2 different projects.
One degree.
Well, folks, my phone shows 104. So by the time I get here, it's going to be 105. So welcome everyone to Master of Science Defense for Prince. So this presentation is it's part of the fulfillment degree requirement in mechanical engineering. So the way it's going to go for the first 40 minutes, 40-ish minutes, Prince will present. Then we will take all the questions from the audience. Then we'll ask the audience, general audience, to leave, and only committee will stay and further ask questions and torture Prince a little bit so before we let him go. So without any further ado, Prince, please.
Hello, everyone. My name is Prince Mehandiratta. I'm finishing my master's in mechanical engineering, hopefully today. I'm doing my master's with a report option. Basically, I'll be talking about 2 projects, but I'm a controls engineer and I do mechatronics stuff. So I'll be talking about 2 controllers, but I'll talk about that. But first of all, I'd like to thanks a lot for my committee members, Dr. Alexander Lebowski, Dr. Scott Cole, Dr. Craig Frederick, and first, last but not the least, I would like to thank my mentor, advisor, and my inspiration, Dr. Alexander Sergey, who gave me this opportunity to learn from him. And for the last 1.5 years, I was working with him, and I got to learn a lot and got so many skills. So my degree is about controls. I designed 2 controllers, and first is about remotely controlled industrial robotic arm, and second is about simulation of automated thermal furnace. They're both not related to each other, but they're related to my work. That's what I do, and I've I'm glad to show you and talk about this project to you guys and see if you can learn something from this. I'll try my best. We'll do some overview of what we're going to talk about today and how it's going to be. First project is about remotely controlled industrial robotic arm, where my work is here. We did a lot of work. Basically, I did a lot of work by designing, making things, and did all the wiring. And you can see, guys, everything you see here is assembled, or every nut here is done by me. So it works. That's the best part. And we will be talking about this thing and what we're going to be talking about today. And so we'll go with the background, how we control industrial robots, and how we're going to use this in our project. And we'll also see what are the current standards, or how robots are being operated in the industry right now, and how people operate or jog robots, and how this thing looks. Then we'll talk about remote robot system layout, which is all about this, and how the entire setup looks like in the lab, as well as how you will be able to control this from anywhere remotely. So I'm going to talk about that. And then result, how will it perform, and what our future work is going to be about, and how people will be able to use this, and what future holds for this project, and how it's going to move forward from here through Dr. Alexander Sergeyev. Two Alex, and so many Alex in this room. So I'm going to talk about second project, simulation of automated thermal furnace, which was funded by ArcelorMittal company. They have their plant in Indiana. They're a steel manufacturing company, and they've sponsored our project. And I'll be talking about that, what their background is, and what their current layout is. So they asked us to help them out with their project, or the problem which they were facing over there. So we were successfully able to do something for them, and they'll be implementing that into their plan soon. So senior design team is working on that. And my part, so this project was 2 semesters long. My project was done last semester, as you all know, that I'm on co-op this semester. So everything that I'm going to talk about was done a semester before. So it was done in last semester. And this project is about 2 semesters. So first portion was done by me and a few people from senior design team who were working with Alex. And I designed and I understood this project, what their demand is, what they're asking for from us, and how we can help them out. So my work was to understand their entire furnace and how I can use their data and guide senior design team to work on that and design a simulation model for that. And what result I achieved, and how that project got finished this semester, and they were successfully able to finish this project, and they're talking to ArcelorMittal company, and they'll be implementing our work over there. So my project is here, and we are going to start with the first project first, and that's how it looks like when it's connected to the robot. That's how industrial robotic arm looks like if you have not seen it before, but I'm sure everybody might have seen it at some point in life. So we all know robots play a key role in the industry right now, and in manufacturing demands robots in today's world, because we need precision manufacturing. We need there are so many things which makes robot very important nowadays in the industry. So the way it's growing, global sales are reaching new heights, new records. In 2017, we sold about 381,000 robots. And the stats by International Federation of Robotics says that it's going to grow. So we need more robotic programmers for sure. We need more trained, more skilled robotic programmers. That's where this project is going to help out. because robots are very, very expensive. As a normal human being, I can't purchase a robot and start practicing in my home and in my backyard and just play around with it. So we need something like this where, or people like Alex who thought about this project where you can use our resources in our lab. We have robots, we have 4 robots which we are teaching, and we need to take credits for that, but there are people who, like in community college, or people who don't have these resources, who don't have a robot in general to learn these things, because we know that this market is coming soon and it's already there, and it's going to reach new heights, and we need more and more trained robots for that. So this project is going to help them out who don't have those resources, and how this project, we'll see how this is going to work. I mean, currently there is no commercially available remote robot available. So there is no manufacturer of. So mainly there are 2 main companies, KUKA and Fanuc, and they're not even thinking about making a remotely controlled robotic arm. So this is something new, which I found out after doing some research that nobody's talking about it so far. There are other type of robots which are controlled remotely. There are drones which are controlled remotely. There are other things, but there is no such remotely controlled industrial robotic arm available so far. So let's see how robots are being operated, first of all, and how we actually jog the robot, or how we actually use the robot, and how we learn or program robots. So I'm not going to talk about the entire 4-credit course over here, but I'm going to give you some overview how we actually use robots. So we connect the robot through this. This is the teach pendant. Like you guys play video games at home, so you need that remote joystick thing. This is our joystick controller. We hold this deadman switch at the back. I'll be talking about that, but I just wanted to show you guys that this is the teach pendant which we'll be using. And the entire project is all about this, not about the programming, how we program or how we do things, but it's entirely about how to control this teach pendant, or how to jog this thing. So also we need a robot for sure, we need a controller, and then we need this teach pendant, and we need operator, somebody to jog the robot. Also, controller does the calculations for robots to calculate how we want to move that. So whenever we press any button, there is a controller or programmer who does all the backend programming and the calculations in order to move all those motors to jog the robot. Just want to bring that out. So on the teach pendant, we have an emergency stop button, which if there is any emergency, you can press this. As you can see in the background, there's a robot moving. That's not what this video is doing, but just you can imagine how the robot moves. There is an on-off switch over here. There's a shift key, which we'll be using. It must be pressed all the time in order to jog the robot in the background. So there is a reset key if there is any error. So you'll be pressing that reset key in order to clear the faults or any alarms. You can also increase or decrease the speed of the robot, how you want to do that. So there are buttons for that as well. There are coordinate keys. That's way deep. You don't want to know that right now, but there are, if you want to jog the robot in like coordinate frames and all access, these are all the keys which you'll be using in order to jog the robot in those directions. So if you want to jog the robot, you will need to hold deadman switch at the back. You will need to press the shift key, and you will be pressing these joint keys. So these are the three things which you need in order to jog the robot. So they have designed these things in such a way that only the person who knows about it can do it. We don't need somebody just messing around and damage the robot or any equipment in the industry. All right, so about our project now. We have the setup where we connect this teach pendant and we insert this thing down there. And if you guys can see, we have all the actuators for all these keys, also for the back keys, which will be down there. So you lift this plate a little bit up, slide it down there, and this thing is being calculated. I mean, you need to do some little bit of adjustment for that, but once everything is settled, all these actuators will be pressing keys over here. That's how basically it works. So we have this entire setup in our lab. We have a PLC. PLC is like a controller which, let me back up a little bit. So we need a computer in our lab. We need a webcam, and we need this teachment for sure. We need the entire setup. All these actuators which you guys see over here are represented by this and this. And that's the PLC which we are looking at. It's connected to all these actuators, so all these outputs will be connected. And we need a laptop connected in our lab, which will be connected to this PLC. And every signal will be sent, if you want to control any of these actuators, the laptop will be sending signal to this PLC, and this PLC will be controlling all these actuators down there. So whatever you press from that laptop, there's a software, so you don't want to delve very deep into that, but the laptop will be sending signal over here, and that will be controlling here. Also, there's a webcam. So the speech pendant also has a display screen. Whenever you jog the robot or do anything, there's a program you can write over here. You don't need a computer for that. So there's a small display screen over here. So I have a webcam connected inside you. We can't see over here, but that webcam is represented by this. We need at least 2 or 3, or you can connect plenty of cameras in order to see how robot is performing. So we definitely need a webcam for this display screen, also for the robot. You can have more cameras as well. So when you have all this data on this computer, you need internet now. And that internet will help you give access to the other computer over here. So that will be remote user. Like, let's assume there's a person who wants to jog robot in our lab. So there'll be a person sitting in remotely, and they'll have access to the robots in our lab. And we have this entire setup. The person will have display of the robot. Whenever you press any button over here remotely, you will be able to see how robot is performing, as well as you'll have a current real-time display whenever you press, whenever the person will be pressing any buttons over here. The real-time display will be shown over here. Like, we have like a virtual teach pendant, which completely represents the screen on a web page. We have a real-time robot display. So basically, you'll be plugging this thing in and sit somewhere else and jog this robot. That's the main goal is. And that's where internet is going to help us out with that. So I designed this SolidWorks model, and everything works. So I think I did a good job in that. We tested our I tested this actuator first of all, and saw that I wanted to make sure that the weight required for pressing these it's not a big deal, but you look at these guys, it's very, very like narrow, and it was a challenge for me to find the right actuator, which one will fit here. And we ordered these actuators from Taiwan. Took a while for us to get them, and then we tested this actuator. It was working, so I designed this thing, the setup in lab, and we made sure that everything is working. Then we ended up designing the whole thing, and it took a while to wire this thing up, and it's a lot of work. Also, I wanted to have it in a professional way because it's a prototype, so I wanted it to be ready for the market. So yeah, that's how the entire setup looks like, and that's the wiring schematic. We use plus 12 volt for the actuators down. You don't want to go deep into that, but we have the wiring schematic as well. That's the Robotron website, which Dr. Alex and Dr. Scott did over the years, and this website helps students to learn about robot programming for free. And we are expanding this project now, and we will be able to help the students or people who want to learn robot programming. They can learn as well as they can test it on the real robot. So that's the end goal. That's how website looks like. When you have the access from us, you will be looking at the screen of the real-time display of this screen when you turn this on and when this robot is connected. That's how the screen looks like, basically, but you'll be able to see that on the website. You'll have all these buttons, which are here, but we didn't want to do anything which is proprietary to Fanuc. So we designed the entire thing on our own, and basically Dr. Scott and his team did a great job helping me out and helping Alex and me out in designing the entire thing and making this thing work. So everything works. That's a real-time demo of making a square. We tested a few more programs, but just a short example how things work. You press keys over here on the virtual key spinning, and you see the real-time display over there. This is the real view how the robot is performing, of course, because it's live feed, so it's going to be same. But yeah, we tested pressing keys. It's all working in coordinate frame right now. So yeah, whatever you're pressing, it's doing things.
So that is not a program that is point to point with the buttons, correct?
I did test the program, but this is just to show that actuators are working.
Mhm.
So that program is made by me on the website, not on the robot. I just wanted to have something running. Future work. Most students to test the project, for sure. You want to make sure that before this product is ready, we have more people to test this thing, and we want to have more feedback from people and make it better. Design a platform for tablets or iPad. You want to have something ready for the tablet or iPad, and you can do it over the small screen and touch things instead of doing it on the keyboard. And so website is secured for the computer, but if you want to move ahead with tablets or iPads or other platforms, you want to have more secure communication protocol, because we haven't worked on that yet. That's my first controller project. Time is good. Second project is simulation of automated thermal furnace. This is, as I said, this is for ArcelorMittal company, and I designed this simulation model for them. Also for my team. So ArcelorMittal company were struggling with some piece. So what they do is they have this furnace which is like 3 times size of this room in Indiana, and what happens is they basically produce steel. So they run the sheet through this cart inside their furnace, which they have in Indiana. So what they do is they weld these 2 sheets, and they run sheets one after the other, and this cart keep moving this roller up back and forth in order to make this motion continuous. And this thing enters into the preheat section as well as radiant heat section. So we are going to be working on 3 sections basically. We have preheat section as well as radiant heat section, and jet and air cool control cool section. These are the 3 sections that they have in their furnace, and our project is basically about 2 of these sections, the preheat one as well as the radiant heat furnace. And they were facing this problem that whenever they weld these 2 sheets, like let me back up a little bit. What they do is they run the sheet inside the furnace, and they increase the temperature of this furnace in order to do some annealing work with the metal sheets, and then they sell this product. But they were facing this problem that whenever they weld 2 sheets, like 2 different sheets, so they run one sheet which requires, like, let's assume 1600 Fahrenheit, and another one requires like different temperature, but they want to have this process continuous, so they weld these 2 sheets in order to make it continuous, and they don't want to stop anywhere in between. So they weld it over here, and that thing helps a lot in making the process continuous, and they don't stop the furnace at all. But they are forced to stop the furnace sometimes whenever there is some faulty piece coming out. So that's where our project comes in. So what the thing is that whenever 2 sheets are welded, I'll talk over here in this diagram. So let's assume that there's one sheet which requires 1750 Fahrenheit, then there's one sheet which requires 22,000 Fahrenheit. So this sheet is running inside the furnace right now. And this is the next sheet which is going to come after this. And these are the burners. So whenever we increase the temperature, we want this one to be at 1750. But problem is that till this point, we want 2000, and right from here, we want 1750. But burners can't respond, or the entire furnace, which is like this size room, it can't change the temperature right away. So it takes a while. So what they do is, like, there is an operator who controls these valves, and they decrease the temperature. By the time it reaches 1750, we are already so late, and temperature reduces from 2000, 1900, 1800. We get here, and then that's where we achieve 1750. So this portion is waste. They can't sell it. That's where they wanted us to understand this thing and what problem they're facing and how we can help them. So my work was to make this thing on Simulink, how the system is going to respond. And then the senior design team were working, I was guiding them how to do that, but they were working on using my model to optimize this entire system, and which they were successfully able to do, which I found out yesterday. So, which is great. I hope I was able to explain this properly. So, in order for me to understand the system, I didn't go there, but they gave me this entire data, which was days worth of data, and I was supposed to understand this thing. And my team was also struggling. We were all struggling, and because these are so many numbers, and those guys never worked on any PLC programming before, and I had a little bit of experience, so I did understand how their entire program, which was very, very lengthy, and I never saw that big program in my entire life, and it was quite a lot of work for us to understand all these variables and then understand what variable plays what role in their furnace, which we have never even seen. So it was a challenge. But my work was just to design a Simulink model for them to understand things, and they can understand, and they can optimize the system. So my work was basically about preheat and radiant tunnel section. So preheat has 5 zones. Whenever I talk about zone, that means that we have this burner which is burning or increasing the temperature or reducing the temperature. So we either close the valves or open the valves in order for burning the flame in order to increase the temperature of that area of that particular zone or decrease the temperature. So in this section we have 5 zones, means 5 burners. In this section we have 8 of them, so we have 8 burners basically. That each burner represents this zone. And I designed the system accordingly, and we send signal, and that system is responding according to the way it is responding in their furnace over there. So we got the data from them, and then we passed the entire data which they gave it to us, which was days worth of data, and we send it through this signal block, and it goes to all these zones, representing that there is a sheet coming in, a steel sheet, which is going into this furnace, and it's giving us some result and how system is responding to that. And similarly, we have 8 of those. For, as I said, we have 5 in preheat and we have 8 in radiant. So we have 8 of these zones, which are shown by red circles. And we have yellow circle plot for signal, which we built from the data which they provided to us. And these blue triangles which you see are showing the scope after passing through this zone and how the system is responding, or basically how those burners are, or those valves are open and closed, and how the furnace is going to respond in that particular section or particular zone of that section. That's how we have all these results for all these particular sections. And we also have the entire result for just making sure that if somebody wants to analyze, so we have one entire scope which gets the result from all these sections, and that's what this thing is doing. About the signal, as I said, they provided us this entire day's worth of data. We compiled the data and made the signal for our model, and we used this model and we ran through our Simulink block, and it was working. That's my main. So when I was talking about burner and valves which are opening and closing, this is what it is representing, and that's my temperature source. That's my thermal reference sensor. What happens is I use PID block, and they already have a program which they provided us, which already had a PID block, and they were running that on auto tune mode. So I designed exactly how it should respond according to their program which they provided to me. That's what this thing is doing with the feedback coming in, and so it was responding accordingly. Also wanted to make sure that when I'm trying, assume that I'm at 1600 degree Fahrenheit and I want to go to 12. Before I do that, I'll show it here. I'll explain it over here instead of going there. So that's how the result looks like, and the signal which I was telling you about, this signal, which is shown by a red line, is represented by the blue line over here. So it's the same signal which I was running in. I use this. So that signal is coming from here. That block has that signal which I designed from their Excel file which they provided to us, and that is going to all of these zones. And I'm having that signal out in one way so that I can check what my real signal was and initial signal was and how the result is going to look like. So when I had the result, I have the initial signal which is represented by a blue line, and I also have the response to the system. So let me explain. I like to understand things with the example. So almost everybody is driving car over here with the cruise control mode, and this is my way of explaining things, how I can explain how the system is responding. So when you guys drive on the road, you want to drive at 50 miles per hour, and you are at 0 miles per hour right now, and you're just starting from home, and you want to achieve that 50. So before you hit 25, the system doesn't allow you to press cruise control or I want to be at 50 right away. So it wants you to achieve at least 25 before you hit cruise control. That's how my car responds. Maybe you guys have different car, but my car responds this way. So that's what preheat section is doing. So when I want my sheet to be at least 1600 degree Fahrenheit, that's what preheat section is doing. My preheat section is 25 miles per hour. So I want to be at least 25 before I do 50 or 60 or 70. So my first preheat section is 1600 degree Fahrenheit. I want all my sheets to be at 1600 degree Fahrenheit before I play around or go up or down over there. So also, when you're driving uphill or downhill and you set your cruise control about 50 or 70, sometimes it goes 52 and then it tries to settle down at 50. Sometimes it goes 48 and it just tries to get settled at 50 miles per hour, not degree. That's what the system is doing as well. It's using PID, and I'm at 0 degree Fahrenheit, and I want to be at 1600 degree Fahrenheit. So sometimes system is doing some overshoot, and then it does some little bit undershoot as well, and then it tries to settle in, and that's where I want it to be. So if you want it to be at 70 miles per hour, it does a little bit 71, 72, and then 71, 70, or sometimes goes 69, then come back 70. That's how this thing is doing as well. You want it to be 1600 degree Fahrenheit. It did a little bit of overshoot and tried to settle in, and then you increase the temperature again in this area, then it started going up because it couldn't settle over there because I added blue line, which is a little bit raising temperature over there. So that's how basically this furnace works. I hope I was able to explain that.
But your air and gas valves are open or shut only?
Yes, that's
Okay.
what I'm going to talk about now.
Okay.
So when I want to see what time when I'm opening those valves and what time I'm closing those valves in order to increase the temperature. We all know if you want to increase the temperature, we open those valves, we start having that flame thing in order to increase the temperature. So in this area, if you see, I'm currently at 0 degree Fahrenheit. I want to go 1600 degree Fahrenheit. So of course, I will open my valves and start those burners in order to really raise the temperature of that furnace. That's what's happening over here. So 1 represents valves are open, and 0 represents valves are closed. And whenever I'm raising the temperature, my valves will be open in this area. As soon as I hit this point where it is already reached over there, it shows this fall over here. That is when the valves are closed. So that's what happens here. And the same way, when I'm overshooting and I want to come back over here, my valve should be closed, and when it settles in, it will be closed. And basically, before I do that, I want to bring this thing up. So I wanted to check the error as well. Like if I am in 20 degree Fahrenheit range, like plus minus, the valve should be able to like stay closed. I don't want like exact 1600 degree Fahrenheit. I want something to be about 1580 to 1620. So that's why I have this block which is calculating that and trying to get the result. When you get here, the things are settling down. That's why all the valves are closed that time. And in that plus minus 20 degree Fahrenheit range, it should still be closed. That's why valves are still closed. And as soon as you see there is some little bit change and you want to increase or decrease the temperature, valves are open and closed accordingly. So that's how the system is responding. Cool. But future work, which was done over the semester when I was gone. So senior design team, Tom and Sawyer were working on this project, and earlier they were using LabVIEW model, but I don't want to talk about their work because that's their work and they have their presentation on Monday. You want to go there and see. But their work was to utilize my model and optimize it properly and they made more modifications to my initial system. So when you see this initial system, whatever I was showing earlier, that's in this block now. They added more features to it, sent it into this, got the final result. They were also able to export this file into a PLC program, which they will be using over there, which is really, really cool. I want to learn that. I will be learning that soon. They used Simulink and they connected that to PLC, which is, I don't know if you guys know about that, but I think it's very amazing. And there's not that many documentation available online for that. So we will be doing a research paper on that soon. So yeah, they were able to successfully convert MATLAB Simulink model to PLC program. They were able to optimize the system, and they have discussed the result with ArcelorMittal company, and they will be moving ahead with the project. We were also able to publish 2 papers so far, and third is about to get published soon. First is about entirely on this project. Second is about our NSF, our initial internal papers, which Alex and I and other members from School of Technology were doing, and we published a paper on that. Also, my second project, which I was talking about, is also going to be published in ASC. We already submitted the abstract for that. Conclusion. I was able to design, develop, and implement remote robot system, which is working. It is working robotic arm, and I did preliminary testing and publication of the projects. I did testing on development and simulation of ArcelorMittal furnace. And I'm going to talk about mechatronics now. So my degree is mechanical engineering. I did my bachelor's in mechanical. I did my master's in mechanical now. And I got some co-op experience in similar work. So currently, as I've worked in the industry for 4 months now, and I've been reading a lot about the industry, I feel like these guys need people who can do mechanical, electrical, computer science. Basically, you should be willing to do and learn new things. That's why we need mechatronics engineers. So I really recommend, and Dr. Alex is starting a new program with Masters in Mechatronics, and there'll be more people like me who can do more mechatronics work, and people can do mechanical as well as electrical, computer, I did wiring, which is electrical. I did some programming on PLC, which is like kind of electronics, electrical. I designed the entire SolidWorks model, this entire system model on SolidWorks, which is mechanical. Did the wiring. Yeah, I did kind of a few things. That's why we need more mechatronics engineers. And after working in my company I work in a PATI engineering company. We work as system integrators now, and I think we need more people who can do mechatronics work. Acknowledgement. Of course, I want to thank a lot to Dr. Alexander Sergey and Dr. Scott Gould and his computer science department. Brandon, who was an undergrad, he graduated. Madeline is still studying or doing her undergrad in computer science. So I want to thank my remote robot team. I would like to thank Machining Shop, Nicholas Hendrickson, Michael Goldsworthy, Ari Cronish. They helped me a lot to make this project, bring this project into life, and whatever we were thinking, whatever we were imagining, or whatever we designed, they were able to make it very precisely, and everything works, so which is great. Also, I would like to thank my ArcelorMittal team, Dr. Alexander Sergeyev again. He helped me a lot in that project to guide me whatever he was expecting. More people. I would also like to thank William Leapack from ArcelorMittal company. He works as a principal engineer in that company, and he was very kind, and he gave us a lot of material to study, and it was really inspiring and it was really amazing to work with him. My undergrad team, Thomas Bricka, Sawyer Paul, Zachary Sargent, and Kai Wilkinson. I'm really thankful to everybody for making my dream come true, and I finished my master's here today.
Not yet.
Thank you.
So you guys can torture him for 20 minutes. So we're open for questions. Please.
Yeah.
What would you say are some of the main safety features for remote users of the robot? Some picture comes in my head as somebody hops on this thing, they start smashing around in cages and stuff.
We discussed about that. Scott and I and Alex, we were discussing about that, and we've actually, to be honest, I didn't do that, but I suggested them, and computer science team did that work, and we made sure that only one person will be connected to the computer who will have this access. So they will be controlling the robot. Nobody else will hack into that system. Also, Fanuc robot has this safety feature. If it actually, so let's assume that this is my robotic arm, and if I hit something, it automatically stops. They have this feature,
Collision
guard feature. Thank you, Alex. They have this collision guard feature, and whenever it touches something, or it will break that, but it won't break itself. So that's what happens.
Is it some type of optical sensor or a force?
It's a force.
Okay.
A force, yeah. And also each robot is enclosed.
Yep.
So there is no human access when the robot runs in
Human
production.
Any other question? Yeah.
Okay, so I have two questions. First, about the actuator selection. I did not understand how you selected the actuator. So you said that you tried different actuators and then actually tried pressing the buttons. I did not understand that.
To be honest, I did a lot of research instead of buying so many actuators and testing them out. I did my research and I knew what my dimensions are. I knew what the force is required or weight is required in order to press those keys. That's how I selected these actuators, basically. What was your second question?
Yeah, second question is about the furnace. I didn't understand the zone distribution. What does zone distribution means? You talked about 5 zones and then 8 zones in the next.
Okay. Before that, I was saying that like as a cruise control thing, where we want things to be at 25 before we do play around with cruise control. So preheat, I'm sorry I didn't mention that. In preheat, all the sheets needs to be about 1700 Fahrenheit or 1800 Fahrenheit or something above 1600. So preheat section only brings all these sheets to be at 1600 Fahrenheit. So preheat section only brings all of them at 1600 Fahrenheit, and whatever you want to do is done by radiant heat section, basically. Yeah.
So based on replicate, so from what I understand, you replicated the actual heating system in Simulink, right?
Yep.
Okay, so based on that, did you come to any recommendations or questions about how they designed their system and how it could be improved to make it more continuous?
Yeah, continuous, as well as I personally wanted them to have more sensors inside there so that they can record that data and adjust the temperatures accordingly. But the problem is they don't have that many risks. They don't have, we talked to them and they said it's hard for them to connect sensors inside the furnace. So whatever they have, that's what we are getting right now. They have thought about it, whatever I was suggesting or whatever we were suggesting to them, they were like, we need to optimize system on the outside side, like we can't do anything inside the furnace right now. So
then also with like the current control system, then is there more room for optimization of that?
Yeah.
Yep,
that's why they hired us.
Okay.
If they wanted somebody to optimize their system and understand things properly,
Okay.
They could have done that on their own, I think, but they're already busy doing a lot of setting stuff, so they wanted to let us learn, and we wanted to do something. So
For the remote robotics,
Yeah.
I know you talked about like how it's used for education. Will that help industry as well? How will that help industry?
excellent question. So the company where I'm working, we work as a system integrators, and that's where I realized that we actually need this in the industry as well, because our initial plan was just to make this product for education purposes, but so where I'm working, we get projects from bigger companies. We go there. So young engineers usually go there. Senior engineer stays at the office, and if young engineer is stuck somewhere and he's not able to figure out something, so senior engineers guide them over phone, or they do some remote access to their laptop to check the PLC programming, not for the robots, but because we don't have any remotely controlled robots so far. So what they can do is we can take the system with us and take it over there. They want to test something, they want to do some remote access to the robot, they can connect this thing to this is a prototype, we don't have like fully fleshed product, but they can make something for system integrators like me, or who wants to go there and connect robot and give the access to the person sitting at the office, and he can see what's going on with the robot. That's where I see. I'm not sure what all places we can implement. I think it has so many, could have so many more applications as well, but that's where I see working as a system integrator right now. Yeah.
For the teaching pendant, so if we have a computer connected to your robotic controller, what does the teaching pendant do specifically that the software can't do on the computer?
There is no computer connected to the robot. Robot has its own controller. Let me show you one thing. So I didn't want to use this picture, but that's how setup looks like basically in the lab. They have a robot, they have cameras, they have the teach pendant which is connected to the robot, and this is the controller. So we are adding more computers. There was no computer earlier. So we are adding a computer which has internet access, which will be connected to the remote user. So earlier there was no robot connected to the robot. So they have their own controller. It is something like that, but different controller, like you have worked on Arduino stuff. So
yes, maybe you should differentiate the purpose of the robotic controller versus the computer. What do you use the computer for?
Okay,
the desktop.
Yep. Robot controller basically, whenever you press something on the teach pendant, it gives those signals to this robot controller, and that controller does all the forward and inverse kinematics for all the joints of this robot, and that's how the robot moves. Basically, that's the work of this controller. But this computer we are using this computer for sending out data for the teachment display as well as this display. These cameras are connected to this computer, not to this phone. That's what's happening here. Yep.
The teach pendant used for teaching the robot.
Yep. Yeah. It's like a joystick for the robot. Yep.
Does this allow people to program the robot, or are they just controlling the robot arm?
Both. You can control as well as program robot. That's why we have this display.
Yeah.
You can jog the robot as well as you can make programs and then keep this teachment aside when you are done with making program and then make it run the robot on auto mode and it will do everything on its own. So this thing is used to save all those points. When you see like in documentaries where robots are working, they use this thing before running it over there, or they can do it on the computer as well. Companies usually provide software to design all those set points. If you have like precise calculations for the location where you want to work, you can design here and have it on a pen drive and download it on just remote controller, and it will do on its own. But people like to play with this.
Does it have a specific language, or?
It is. There is a different type of language. Yep. It is very easy language, I think, if you have any programming background. I personally learned this programming on my own. Alex gave me all this study material and I was sitting in lab because I wanted to learn robotic programming, and I learned this programming on my own. So you see this this program over here. It basically records set location points. So you jog the robot over there and then record that point. You jog somewhere else and then record that point. So when you saw that square box thing, whatever it was making, you can basically save points on that piece of paper for a box, and then play the button and it will do on its own. You don't have to keep jogging the robot in order to make a square. Yep.
Yeah, it's called Carol, the language Carol.
Yeah.
So what is the safety feature? So if someone is remotely accessing this thing, what's the safety feature? Do you require a login to access this remotely, or so is it open for everyone to access? And if not, how do you control that?
So the current scenario is where you will go on our website and you will request a time slot from us, and then we'll approve that internally, and then we'll make sure that everything is connected properly and everything is working correctly. And then you get an email notification that everything is all right. You can log into the website again, and you will be able to see this web page, which you won't see before that. As long as until you get our approval from us, you won't be able to see this web page. You will just be able to learn programming and read about it. Great question, guys.
So it's for a particular time slot, though. Like
Yes.
They'll have some
Yep.
identification, and then once the time's up, it'll just kill or something.
Yep.
What was the biggest challenge that you faced in the robot project?
Timing was something for me because I wanted this project to be done soon, and I usually like to work overnights and stay in lab. Internally, I wanted this project to be done over the summer or before summer, but according to Alex, I was supposed to finish it this semester, which I was able to finish earlier, I think. But yeah, timing was the issue. I think I wanted to have this project done earlier so that I could have worked on more projects, I guess. Also, finding actuators was a bit of a challenge because we were getting these actuators from Taiwan or countries from like somewhere from Asia. We couldn't find anything over here which could work for this particular dimensions and all that stuff.
Yes, I'll have my difficult questions for you during the closed doors, but the easy question that I would like you to address, could have you done this in a much simpler way. Why you didn't do that?
I had more ideas on how to control all those actuators, but I think this is the best way for me, at least.
So if you look at the teach panel that has the port,
Yeah.
right, electrical port, we could have fed all the signals, all the electrical signals through the adapter. Why you didn't do that?
So that's one of the easier ways which industry can do, like the robot manufacturer can do, but they have this proprietary issues. We can't open that controller. We can't open this thing. We wanted to make something which is non-destructive, which doesn't harm any of these keys or any of their hardware. We didn't want to open any of these screws because if we do that, we will lose the warranty and they won't help us with anything. So we wanted to make something simpler and just press this button instead of going down there, because we could have done that as well, but this is the right way to do it for us. Otherwise, they could.
Otherwise, he'll be in jail now.
Yeah. Yep.
Also, future possibly approaching companies about doing, like, making partnership to have onboarding. Is that something that you would want to, that might be desirable to progress towards? People are open to?
I would love to do that. I think there is a possibility for that because, as I said in the beginning, there is a huge demand for robotics engineers and we need more people. So that could be future work for more students to contact and partner with more companies and teach robotic programming through this.
On a different angle on that question, do you think it would be in the future possible to work with the robotic company itself to have that remote functionality built into the controller directly?
Very good.
I see that happening. If they will buy us. I mean, they will have to buy from us because this is our idea. They'll have to,
No, he's asking a little bit different question, I guess.
Yeah, I know. I think, yeah, there is possibility in that companies will start doing that. Sure. With time, it will take time.
And actually, I think the big picture behind this project was to show the robot manufacturer that all the advantages of remote control for the robots. You know, this is definitely not the best way. It's a proof of concept. The easiest way would be to build the adapter between that electrical port on the teach pendant, you know, and have that adapter available even for purchase. You know, it could be sold by Fennec. But of course, you know, they're trying to sell more and more robots. So our goal was to show the possibility and advantage of having this for educational purposes and maybe even for industrial.
And you could show that to Fennec and embarrass them into not allowing you to do it the other way. Right?
Well, I already showed one of the integrators.
So they wouldn't let you get into their robot, so you're just like, fine, I'll just control it from the outside.
Yeah.
Reverse engineer.
Happy that everybody's fine, so went well, I guess. Any other questions?
Well, let us thank the speaker again. And I guess that we would like to ask the committee to stay and everybody else, please.
Please grab some food.
Did you bring the coffee? Yeah.
There you go. Thanks. You're good. Let's see what size house.
That's the ground.
Yeah.
It was like,
Good job.
Well, folks, please, if you have any questions to Prince?
I have one.
Okay.